So far, we have done so many things using forces in previous lessons and videos, but we haven't defined what force really is, or at least know how communities of people in physics give meaning to this quantity, force. I'll deal with that in this video. Let me just make my cursor a little bigger here so that you can easily recognize whenever I point something on screen. All right, here we go. So apart from its influence on work done, the other things we know, stuffs related to force are inertia. We also covered acceleration and the event where forces are produced. We call it interaction. These ideas or concepts are summarized by Newton when he formulated the three laws of motion. Now, before we can give meaning or define force, let's just recall that in the law of interaction or the third law of motion, each time we have an interaction between two things, we get a force. Actually, two forces, a force pair, action-reaction pair, as many people call it, and that this pair of forces has equal magnitudes but opposite in directions. One is acting on the other, and the other force is being applied on the other one. Either one of these forces. That one being applied to the object itself, say this force. And this force could make an object accelerate, and we quantify this effect of force using the second law formula. A, or the acceleration of the object, equals force on that object divided by the object's mass, like that. As explained in the previous lessons, this F here in this formula should be interpreted as the resultant force, meaning consider all forces on the object and add all those together. That's the reason why you also have a chapter in physics about vector addition, because force is a vector. Now, this resultant force, if you get zero, meaning no resultant force, it follows from the formula that acceleration is also zero. The object will not change its velocity. It will maintain its current state of motion unless there is already a non-zero value of resultant force. The object with mass, in this case, will continue moving at a constant velocity. Equivalently, we can also say that it will be moving with the constant momentum. Alright, so momentum. You can look at momentum as something a moving object possesses when there is no force around that is acting on it. If you have an object with mass m here and the object has velocity v, momentum is just the product of these two quantities, mass and velocity. mv equals momentum, but we cannot use m as a symbol for momentum because m has already been taken or assigned to mass. Let's just erase this. And a long time ago, people used I to represent momentum, which basically came from Newton's word in his book. The word was impetus. He used this when he was talking about this quantity. However, it's kind of confusing with the other symbols used in maths and physics, like the imaginary number, which is also I. So people change this symbol for momentum using this letter P as symbol for momentum. Most institutions are using this symbol, and we will be using the same. All right, P. Now, for its units, momentum has kilogram for mass and meter per second for the velocity. All right, as for the type of quantity, we know that velocity is a vector, and because this vector is multiplied by mass, which is a scalar, then momentum must be a vector as well. Whatever the direction of the velocity, it is also the direction of the momentum. Now, let's go back to the question again. How is this related to the definition of a force? Let's start with what we know, all right? From Newton here, F is equal to ma. Also, we learned that this a, or acceleration, is equal to this quantity, final velocity minus initial velocity divided by time, from the definition of acceleration, which is rate of change in velocity. We just have t here, or whatever final time you have. This is in the assumption that we started our observation of things from the time equal to 0, alright? Doing the maths in this equation, we will have this, okay, by distributing the mass m, like that, divided by time. Now, take a look at these products here, mv and mu, mass multiplied by velocity. These must be momentums, or in other references, you may call it momenta as a plural for momentum. Alright? So now we can just write the equation like this. Final momentum minus initial momentum. over time. And that this difference in momentum, following the way we write change in quantities in symbols, we have this F equals delta P, change in momentum divided by time. Now, this is also rate, same meaning as in the definition of acceleration here, time rate. I know most of you at this point still have the idea that a force is a push or a pull. But now with these ideas presented on your screen, we can have a formal operational definition of the force, which is the change in momentum over time, or equivalently, the rate of change in momentum. Remember guys, do not say rate of change in momentum over time. That's redundant, not correct. Use either change in momentum over time or rate of change in momentum. From the formula here, this change in momentum can also be quantified using the product of force and time. See that by cross multiplying, we have Ft equal to change in momentum. This is actually another term in physics, just for your information, from the English equivalent of the word impetus, which is impulse. Okay? Force times time is the impulse. Alright, let's move further to other ideas about momentum. Say we have these two objects, gray and red objects. With this having mass m, let's use subscript 1 for this, and this has mass m sub 2. These two are moving with some initial velocities u sub 1 for object with mass 1, and u sub 2 for the other object. They are moving toward each other, the red object to the left and the gray heading right. Now, the first law says that these objects must have constant momentum at these points. Momentum to the right for this and to the left for this. Constant momentum until they interact by collision and exert force to each other, like that. This interaction gives rise to a force in this direction exerted on red object by gray object, and another force here exerted by the red object on gray object. The third law tells us that these forces must have equal magnitudes but directed opposite each other, as indicated by the negative sign in the equation here. Now, with the second law, you know that F is equal to ma. But equivalently, we can also say that F is the change in momentum over time. You can consider that as another way of stating the second law. So for the first force, we have this delta P over T equals the negative of the rate of change in momentum in the other. Now, these t's here are the times of impact. The time it takes for object 1 to change the momentum of object 2 is the same as the time it takes for object 2 to change the momentum of object 1. Okay? So we can just erase that one. Alright? I'll color this portion of your screen so that we can have more focus on stuff I am about to write. Alright? Here, now let's talk about the principle of conservation of momentum. If we have a closed system, or you can say that the two objects here are isolated from other things around, just the two of them, momentum is conserved. We already know that the change in momentum of object 1 is equal to the negative of the change in momentum of the other, and that after collision, the final momentum of this object, this P, changed from the initial momentum before collision equals the change in momentum in the other, like that. But note that there's a minus sign, that red one in the equation, which implies the need to change the signs of the momenta at the right side of the equal sign. This becomes negative and this becomes positive. I use hyphen here or prime to say that those momenta are initial momentum of each of the objects. If we are then to combine all these momenta before collision and all these momenta after collision, we will have this equation saying that in a closed system, closed guys, okay, isolated, there are no other external forces here. In this case, the total momentum before collision, this, equals the total momentum after collision, this one. Okay, that's all for now. At this point, we need to do some drills and practices to get more familiar with the concepts from the video. We stop here for now and I'll give you other ideas related to what you learned today some other time. Bye.